is Janet and Rabia.
Welcome to Everest Physics Academy.
Before we start, we'd like to recommend our Everest Physics books for high school,
where you can find more explanations and solve applications and the problems. In this video, we are going to write the expression of the voltage across a coil crossed by its own magnetic flux. Explain the role of the coil. Explain the power distribution in a coil crossed by a magnetic flux due to its current. And give the expression of the magnetic energy stored in a coil.
Expression of the voltage across a coil. Look at the circuit. A coil whose terminals are A and D is oriented positively from A to D. Then UAD is equal to RI minus E. Remember, when we write the expression of the voltage across the coil, we pay attention to the chosen positive sense but not to the direction of the current. Now, the self-induced electromotive force is equal to minus L di by dt. This is going to be UAD is equal to RI minus into minus L di by dt. This is going to be UAD is equal to RI plus L di by dt.
Now, referring to this formula, the potential difference across the terminals of the coil in this figure is given by Ri plus Ldi by dt. Steady state. The previous video shows that the steady state is attained when the current becomes constant. So di by dt, or the derivative of the current with respect to time, becomes equal 0. If we replace di by dt by 0 in this expression, so the potential difference across the coil in the steady state is equal to R times I. But we know that the potential difference across a resistor is equal to Ri. So we can conclude that the coil acts as an ideal resistor of resistance R in the steady state as shown on the figure. Purely inductive coil. What do we mean by purely inductive coil? We know that the real coil is characterized by its inductance L and its internal resistance R. However, if the internal resistance of the coil can be neglected, in this case, the coil is said to be purely inductive. So what is the consequence of a purely inductive coil in the steady state? We know that in the steady state, the potential difference across the coil is equal to the internal resistance of the coil times the current in the coil. Now, if we replace R by 0, so the potential difference across the coil in the steady state becomes equal 0. And we know that the voltage across a connecting wire is equal to 0. Finally, we can conclude that the purely inductive coil acts as a connecting wire in the steady state as shown on the third figure.
Let's move to the role of the coil. Look at the figure. We have a coil whose terminals are A and D, and it carries a current from A to D, and the chosen positive sense is also from A to D. Now, let's study this case. If I increases with time, this means that di by dt is positive. The expression of the induced electromotive force is equal to minus L di by dt. L is a positive quantity, di by dt is positive. This means that E is negative. Now, if you look at the figure, I is positive. If E is negative and I is positive, then EI is negative. And if EI is negative, then the coil acts as an electrical load. In some references, the electrical load is called a receiver. Now, look at the figure. So, we replace the coil by a series combination of an internal resistance R and an ideal battery of electromotive force E. And the figure shows that the current flows into the positive pole of the ideal battery. This is because the coil acts as an electrical load, which means that it consumes electric energy. Let's move to the second case. If I decreases with time, This means that the time derivative of I is negative. Again, let's move to the expression of the induced electromotive force. L is positive, di by dt is negative. This means that E is positive. Again, I is positive. Therefore, EI is positive. In previous episodes, we discussed this case when EI is positive, the coil acts as a generator. Look at the figure. We replace the coil by a series combination of an internal resistance R and an ideal battery of electromotive force E. And look at the current. It flows out from the positive pole of the ideal battery, which is opposite to the second figure here, because we have a coil acting as a generator. Now, what if I is constant? If I is constant, then di by dt is equal to 0, which means that E is equal to 0. In this case, the coil acts as an ideal resistor, and if we want to draw it, we replace the coil by an internal resistance R.
Power distribution in a coil crossed by a magnetic flux due to its own current. By referring to this figure, the positive sense is oriented from B to A, so the potential difference across the terminals of the coil is given by Ri minus E, but E is equal to minus LdI by dt, therefore UBA is equal to Ri plus LdI by dt. Multiplying both sides by I, this is going to be I times UBA is equal to Ri squared plus Li di by dt. During the growth of the current, or when the coil acts as an electrical load, or when it receives electrical energy from a source of electromotive force, we can write P total is equal to P lost plus P magnetic, where I times UBA represents the total electrical power received by the coil, and Ri squared represents the loss in the power of the coil due to Joule effect. Now, Li di by dt represents the magnetic power in the coil. Pay attention to this remark. Observe the figure. The current flows in the positive sense, so I is greater than 0. And the coil acts as an electrical load, and the current flows from B to A, so UBA is also positive. Then I is positive, UBA is positive, therefore I times UBA is positive, which represents the total power received by the coil. Now we can write I times UBA is the total electrical power received by the coil during the growth of the current. Ri squared is the loss in the power due to Joule effect in the coil, and the magnetic power is equal to Li di by dt. But L di by dt is equal to minus E, so the magnetic power can be written as minus E times I. The magnetic power is also called the rate at which the magnetic energy is stored in the coil.
Focus, please. This is important.
Now, we want to determine the expression of the magnetic energy stored in a coil. Now, to do this, we need the expression of the instantaneous power. The instantaneous power is given by P is equal to dW by dt, where P is power and W is energy. This is a general formula. Rearrange. So dW is equal to P dt. Take the antiderivative of both sides of this equation. This is going to be the antiderivative of dW is equal to the antiderivative of P dt. Now, if you want to determine the expression of the magnetic energy, you need to take the antiderivative of the magnetic power. The magnetic power stored in a coil is equal to Li di by dt, as we have seen in the previous slide. So replace P in the above equation by Li di by dt. This is going to be the antiderivative of Li di by dt times dt. dt cancels out. This is going to be the antiderivative of Li di. Now, L is constant, so it stays the same. The antiderivative of I with respect to I is equal to I squared over 2. So this is going to be W equal 1/2 Li squared plus constant. Now we need to calculate the constant. When I is equal to 0, W is equal to 0. The coil does not store magnetic energy yet. Now replace I by 0 and W by 0 in this equation. This is going to be, so 0 is equal to 0 plus constant. Therefore, the constant is equal to 0. And the expression of the magnetic energy stored in a coil is 1/2 Li squared.
By referring to the expression of the magnetic energy stored in the coil, which is equal to 1/2 Li squared, during the growth of the current increases, then W increases. Therefore, the coil stores magnetic energy. When the coil stores magnetic energy, we can write it acts as an electrical load or receiver. During the decay of the current, I decreases, then W also decreases. Thus, the coil restores or supplies its magnetic energy to the circuit. So in this case, it acts as a generator. At the end of the growth of the current, or when the steady state is attained, the current becomes maximum. So the magnetic energy stored in the coil is called the maximum magnetic energy stored, which is equal to 1/2 Li maximum squared. Finally, at the end of the decay of the current, or when the steady state is attained, the current becomes 0. So in this case, the magnetic energy stored in the coil is 0. The aim of this experimental simulation is to verify that a coil stores magnetic energy during the growth of the current. For this aim, we use a battery, an SPDT switch, an ammeter, a resistor, a coil, a lamp, and a convenient apparatus used to show the current in the coil as a function of time. We start the simulation by turning the switch to position 1. So the coil, the resistor, the ammeter are connected in series across the battery, and the lamp now is outside the circuit. Look at the curve. The current starts 0 and increases to a certain value, and the coil stores magnetic energy. When we turn the switch to position 2, the coil, the resistor, the ammeter now become in series across the lamp, and the battery is disconnected, or it becomes outside this new circuit. So look carefully to the lamp when we turn the switch to position 2. We notice that during the decay of the current, the lamp glows for a short time interval and then it dies out. So we can conclude from this simulation, during the decay of the current, the magnetic energy stored in the coil is converted into electrical energy, and part of this electrical energy is consumed by the lamp and it glows. Thank you for watching. If you like this video,
Subscribe to the channel, hit the like button, and share.